on Leo Szilard. Leo Szilard was one of the most remarkable minds of his generation in the 20th century, and a unique personality in physics. He changed the course of history for the United States, and most people do not know very much about him. We're having this session today to help rectify that, and we're fortunate to have three speakers who have expert knowledge about Szilard. The first is William Lanouette, he's an author, and as we heard last night, he's also a playwright. He's a public affairs analyst who spent 15 years working with the government's General Accountability Office. He has written for numerous magazines and journals. He has served as a professor of public policy at a number of universities. He received his PhD from the London School of Economics for a most interesting thesis topic, the use and misuse of science by politicians in the United Kingdom and the United States, a topic which is extremely timely today. Let me introduce William Lanouette. Let me click it on for you.
Okay. Great. How about the tie? That's a good place for it.
Well, if it doesn't.
Good. And this will go here so I don't tear it apart. Thank you very much, Dan. It's an honor and a pleasure to be here to talk about my favorite Hungarian and my favorite Martian. And I want to begin by thanking the APS for this honor to be here and for their generosity in honoring the memory of Leo Szilard. This year marks the 50th anniversary of Szilard's death and the 75th anniversary of the letter he wrote for Albert Einstein proposing to Franklin Roosevelt the danger of German atomic research, and eventually leading to the Manhattan Project. But the APS also should remember this is the 40th anniversary of their Leo Szilard Lectureship Award that recognizes outstanding accomplishments by physicists in promoting the use of physics for the benefit of society in such areas as the environment, arms control, and science policy. And for those counting, it happens to be the 80th anniversary of Leo Szilard's patent of the nuclear chain reaction. Szilard should also be remembered for his many insights, both in physics and biology, and for his historical initiatives to control the nuclear weapons he worked so hard to create. We should also remember him for his sense of humor. Here are some highlights from an amazing life. Born in Budapest, Hungary in 1898 to an assimilated Jewish family, Szilard was tutored at home until high school, giving him a flair for independent thinking. Bright and precocious from an early age, he grew up thinking he had to save the world and always sought a narrow margin of hope when doing so. In 1919, when the fascist Horthy regime barred Jews from Hungary's universities, Szilard vowed to study in Berlin. He arrived there at age 22 and found himself at the epicenter of modern physics. He decided to abandon engineering at the Technische Hochschule and instead took up physics at Berlin University, where he encountered Albert Einstein, Max von Laue, his thesis advisor, Walter Nernst, Francis Simon, Max Born, James Franck, and Max Planck. Not bad company for a young kid. But he was undaunted by these luminaries, many already Nobel laureates. To register for a course, then you had to meet with the professor and have him sign your student book. So he went to Max Planck to take his course on quantum theory. But he announced to Planck, "I only want to learn the facts of physics. I will make up the theories myself." At a weekly physics colloquium, he struck up a friendship with Einstein, walked him home frequently. They lived in the same neighborhood. They struck up quite a comfortable friendship. They were both lateral thinkers and both a little bit on the edges of society. And he had a marvelous friendship and collaboration for the rest of his life. Szilárd even persuaded Einstein to teach a course in statistical mechanics to a few friends from Budapest. Well, these friends included John von Neumann, father of modern game theory and computers, and two future Nobel laureates, Eugene Wigner and Dennis Gabor. During the Manhattan Project, 4 Budapest scientists were known as the Martians: von Neumann, Wigner, Szilárd, and Edward Teller. Why Martians? Well, everybody concluded that they were superhumanly intelligent and certainly spoke an unearthly language. Szilard's doctoral thesis applied entropy to information, laying the foundations for what became, in the 1950s, cybernetics or information theory. And I look forward to what Dick Garwin has to say on this topic. Szilárd loved inventing things. In the 1920s, he brainstormed with Dennis Gabor on the idea of an electron microscope. It was later designed by Gabor's teachers, so instead he went on and won a Nobel Prize for inventing holography. On his own, Szilárd devised a linear accelerator, and years before E.O. Lawrence built one in Berkeley, Szilárd designed a cyclotron. There's a model of it at the Smithsonian in Washington, D.C. Also in the 1920s, Szilárd and Einstein filed 30 joint patents on a refrigerator with no moving parts. It was cooled by an electromagnetic pump, and a liquid coolant transferred the heat and the cool. This proved too noisy for kitchens, but in the 1950s became the cooling mechanism for the nuclear breeder reactor, a power plant that's supposed to make more fuel than it consumes, and which Szilárd also happened to have thought up and named during the Manhattan Project. I got interested in Szilárd because I was writing a piece for The Atlantic about the breeder and looking at the history of things, and the first breeder was named after Enrico Fermi. I said, what happened to our friend Mr. Szilárd? That got me on his trail so many years ago. In Berlin, Szilárd taught seminars and courses in physics with von Neumann and Erwin Schrödinger, and he had planned to teach one with Lisa Meitner, but then he fled Berlin for London in 1933 after Hitler took power. His friend Hans Bethe knew him in London and said of Szilárd, he was one of the most intelligent people I have ever known. His mind worked quickly and profoundly, and he was able to come to ideas that most of us appreciated only after many hours of talk. This was his strength and, of course, also his weakness. He was always ahead of his time. His ideas often were expressed in paradoxes, and the paradoxes were not always understood. In Berlin with his friend Max Delbruck, Szilárd became fascinated with biology and thought it would become the next theoretical science after physics. When he settled in London in 1933, he helped find jobs through the Academic Assistance Council, which he helped create for all the refugees coming out of Germany. Then he turned to A.V. Hill, himself a physicist who had become a biologist, and wanted at the University of London to study biology. But before he could get into this new field, he thought of two concepts that changed his life and the world. One was the nuclear chain reaction, and the other was critical mass, to start and sustain it. Szilárd didn't get back to biology again until 1946. Immediately, Szilárd saw the chain reaction as a way to generate electricity and to make A-bombs. He patented the chain reaction in 1934 and had the Admiralty make it a secret lest German scientists see its military potential. For the next 4 years in London, Oxford, with trips to New York, he was searching for the element that would produce his chain reaction. His patent had mentioned 3, beryllium, indium, and uranium as possibilities, but he never got a chance to do much testing of any of them. Szilárd was always politically astute, And when living in London, he vowed to move to the USA a year before the war. So in 1938, he took an ocean liner and moved to New York City. In 1939, he met Nobel laureate Enrico Fermi at Columbia. There learned that uranium was the element he was after, and that summer they co-designed the world's first nuclear reactor. Then he went to tell his friend Einstein about chain reactions. Einstein's response, I haven't thought of that at all. And of course he hadn't. But he trusted Szilárd and liked him. He was also as political as Szilárd was. And the next, Szilárd proposed and drafted the letter to President Roosevelt that warned about the German A-bomb program and urged an American response. Now, Szilárd succeeded where German scientists failed by recognizing you need pure graphite as a moderator in order to create a reactor. Impure graphite contains boron, which soaks up the neutrons. Szilárd knew that and ran around to get the graphite he needed for the work at Columbia that was 99% pure. The Germans tried the same thing with impure graphite, and when it didn't work, they went to heavy water as a possible moderator. Einstein's famous letter led eventually to the U.S. Army's Manhattan Project that created the world's first controlled nuclear chain reaction in 1942, and the first A-bombs in 1945. After their reactor first worked, Szilárd shook hands with Fermi there in the squash court under Stagg Field, and he said, this day will go down as a black day in the history of mankind. He was always looking ahead and always fearing, if not the worst, at least something awful over the horizon. During the war, he worked eagerly to build the A-bomb, but then became ambivalent and worried about post-war arms races and controls. In 1944, though, he thought the A-bomb should be used on cities to shock the world, thought the shock was necessary to create the kind of international control that he sought after the war. But by early 1945, he abandoned that idea. He knew Germany was clearly defeated, and he tried 4 ways to stop the bombing of Japan and to, he hoped, prevent an arms race with Russia. First, in March of 1945, he had Einstein send another letter, now the 4th, to Roosevelt, urging the president to meet with Szilárd about post-war controls of this work. But FDR died in April, never saw the letter. Second, in May, he took that letter and a memo he had drafted to the Truman White House and was sent, to his mystification, to Spartanburg, South Carolina, to meet James F. Burns. Szilárd took along another Manhattan Project scientist who had opposed the bomb by this point, Nobel laureate Harold Urey. Burns was then Truman's representative on the secret interim committee to decide how to use the bomb, and he was about to be named Secretary of State. He told Szilárd he was eager to use the bomb before Stalin's promise to enter the war in August 1945 and to make the Russians more manageable after the war. Besides, Burns confessed he feared that Congress would go crazy if they knew that they had spent $2 billion behind their back and had not used this weapon. Walking to the train station after that meeting, Szilárd said, I was rarely as depressed as when we left Burns's house and walked to the station. I thought to myself, how much better off the world might be had I been born in America and become influential in American politics, and had Burns been born in Hungary and studied physics. In all probability, there would have been no atomic bomb and no danger of an arms race between America and Russia. Failing with Burns, he then went back to Chicago and helped draft the Frank Report by Manhattan Project scientists to the Secretary of War, urging that they demonstrate the bomb before using it on civilians. Fourth, in July 1945, days before the bomb was first tested in New Mexico, Szilárd tried a final desperate way. He drafted and circulated a petition to the president, urging moral consideration before using it on cities and advocating international control. In all, 155 Manhattan Project scientists signed it in Chicago and in Oak Ridge. It was also taken to Los Alamos, but Oppenheimer prevented its circulation. The Army was suspicious when they knew this was coming up the chain of command, so they had a poll of the scientists to find out what they thought, and discovered, to their chagrin, that 83% of the project scientists wanted some kind of a demonstration before using the bomb on cities. When Hiroshima was bombed, Szilárd said he felt a sense of relief. Why relief? Well, at last he could discuss this with the public, educate the public about the threat of nuclear proliferation. But when he tried to publish his petition in Science magazine, General Groves, his nemesis all through this period, stamped it secret, so it couldn't be published. And it wasn't declassified till 1963, the year before Szilárd died. After the war, Szilárd said the most powerful weapon to come from the Manhattan Project was not the A-bomb, it was the secret stamp. After World War II, Einstein said he really only acted as a mailbox for Szilárd, but he did join Szilárd, Yuri, Hans Bethe, Victor Weisskopf, and others in the Emergency Committee of Atomic Scientists to try to educate the public in the 1940s about nuclear proliferation. In arms control efforts after World War II, Szilárd tried to enlist private meetings among US and Soviet scientists, thinking that their reason could somehow influence the leaders of their respective countries. He wrote an open letter to Stalin urging that the leaders give radio broadcasts to each other's people. And since '57, he was an active participant in the Pugwash conferences on science and world affairs. In a private 2-hour meeting with Soviet Premier Khrushchev in New York in 1960, Szilárd gained his agreement to a Moscow-Washington hotline. And in '62, he founded the Council for a Livable World, the first political action committee for arms control, initially trying to elect senators to favor nuclear arms control treaties. He thought the power of arms control negotiation was in the hands of the Senate. In 1960, when diagnosed with bladder cancer, Szilárd obtained isotopes from his friend Maurice Goldhaber at Brookhaven and devised an irradiation technique that eliminated the disease. He was shy, witty, eccentric. He wrote The Voice of the Dolphins, a political satire, in 1960 that predicted when in the 1980s the US-Soviet nuclear arms race would also wind down. A 1947 satire, My Trial as a War Criminal, about scientists' responsibilities for their weapons of mass destruction, is credited with prompting Andrei Sakharov to the heroic political activities and activism that earned him the Nobel Peace Prize. The biologist Francois Jacob calls Szilárd an intellectual bumblebee for the many novel ideas he shared. And James D. Watson said that for intellectual stimulation, he loved being around Szilárd because, as he said, Leo got excited about something before it was true. In biology, Szilárd proposed the European Molecular Biology Organization, modeled on CERN, and helped create the Salk Institute for Biological Studies, where he was one of the first fellows. He was the first to devise a way to clone living mammalian cells, and he saw that enzymes control their growth by an on-off process called negative feedback. This insight gained Jacob and others the Nobel Prize, for which they credited Szilárd in their speeches in Stockholm. Szilárd's studies of cancer, aging, memory are praised today for their early insights. And ever the contrarian, he also proposed that scientists be limited to publishing only 100 papers during their whole careers, forcing them to decide which ideas were most important. He wrote delightful children's stories and clever science fiction, even composed his own 10 Commandments. Instead of honor thy father and thy mother, he said, honor children, listen reverently to their words, and speak to them with infinite love. Instead of thou shalt not bear false witness, he said, do not lie without need. And instead of thou shalt not kill, he said, do not destroy what you cannot create. The energy activist Amory Lovins told me that he once studied piano with a friend of Leo Szilard's, and one day Szilárd visited the home of the teacher. I had a wonderful encounter there with Szilárd sometime between 55, 57, I was 8 or 10, And I asked him why the sky is blue. He gave a good physics answer. Szilárd said, because the sunset is red. I gave him to understand that he wanted perhaps a better why answer than that, so he mused for a while, then he replied, well, my boy, I'm sorry, I can't tell you that, not because you're not old enough, but because I'm not old enough. Szilard's many questions and ideas continue to challenge us to defeat Maxwell's demon in a thought experiment in the 1920s on entropy and information. Szilárd had invented the Szilárd engine, a process for manipulating molecules. And today, the physicists Mark Raisin and his colleagues at the University of Texas are using that Szilárd engine concept to separate isotopes and control atoms in small groups or even individually. The Einstein-Szilárd refrigerator also survives. Small-scale working models are being run by Malcolm McCulloch at Oxford and Andy Delano at Georgia Tech. When a fellow at the Salk Institute in San Diego, Szilárd began seminal papers on memory and recall and began planning with Salk an ambitious study of the human brain. He told friends living in San Diego was a foretaste of paradise, and he loved brainstorming with others at the Salk, Leslie Orgel, Melvin Cohn, Francis Crick, Jacob Bronowski. The Szilárd papers are going to be digitized thanks to a grant from the National Archives, and in about a year will be available and searchable online. That's the good news. The bad news for any researcher is you don't have an excuse to go to San Diego. But all this ended too soon, and on May 30th, 1964, Szilárd died in his sleep of a massive heart attack. At a memorial service at the Salk Institute, Jonas Salk said of Szilárd, his interest in peace and in the problems of disease were all of one piece. As we have said, he was a humanist with a powerful intellect, but also a man with a warm heart. In his eulogy, Ed Lennox marveled at Szilard's heroic and ingenious recovery from cancer, then wondered why he had not been as successful with that heart attack. Lennox could only conclude, God never would have got Leo if he had been awake. After the service, Szilard's friends chuckled when they heard about his idea for scattering his ashes. Put them into brightly colored balloons, he told Orgel, and release them over the ocean, and that way at least it will delight all the children. In 1998, for the Szilárd centenary, Szilard's ashes, which had been sitting on a shelf in San Diego, were divided. Half went to the Kerepesi Cemetery in Budapest, the other half to his wife's family's plot in Ithaca, New York. And in Ithaca, New York, they put some ashes into an airmail envelope, and they launched them towards the Atlantic. In closing, I'm going to raise a what if. Just before he died, Szilárd began correspondence with two very notable and interesting people. And I wonder, what if some collaboration had pursued? The first person he wrote to was the philosopher and mystic Thomas Merton. The second was Dr. Seuss. Thank you. Now I have some slides, and I'm not sure if I can show them. And do I have time?
Yes, you do.
Okay. I brought along a little gallery of Szilárd pictures. Then I just hit the advance button once it goes.
Yes.
There we go. Yeah. I'll just throw these up. They're in no particular order, thanks to the haste of my arrival here. But let's see, that's how I do it. Okay, here he is when he was about 16 with his favorite hat. He'd like to be different, even as a kid, and he loved this hat. But when living in Budapest, he went one day with his brother Béla to the zoo, and the hat was blown into the rack by the moat by the elephants, and he fought with an elephant and lost the hat. So he had to get himself another hat. This is the iconic picture. It's actually posed for a 1946 movie of Szilárd and Einstein drafting the 1939 letter to FDR. This was the Pugwash Conference in Stowe, Vermont in the 60s with Henry Kissinger and Eugene Rabinowitz. Szilárd loved the Pugwash conferences, especially kibitzing with scientists from all over the world. This is the last photo taken of Szilárd at the Salk Institute in the spring of 1964 during one of the seminars. This was taken in 1935 in Washington, D.C. At the National Academy of Sciences. And he knew what Lawrence didn't know, which was that chain reactions were a possibly dangerous idea. Why he posed with that secret finger at his lips, I'm not sure, but it certainly shows the state of physics knowledge at the time. Here he is in the late 50s in Boulder, Colorado at a conference, a biology conference. On the right is Leslie Orgel, and the center is our speaker here today, Matt Meselson. This is a cartoon that was done for the review of my book, Genius in the Shadows, by the New York Times, and it shows Szilárd with his dolphin for the voice of the dolphins, his political satire, and of course also a bomb. He loved to sit in the tub and think up ideas. And when Julian Huxley came to a Darwin celebration at the University of Chicago, he stayed at the Quadrangle Club and learned that it was a room that Leo Szilard used, and the next morning came out bragging about he had soaked in Leo Szilard's bathtub, so he's probably going to get some new ideas. This was in 1949, and it's a roundtable broadcast with Harrison Brown, Fred Seitz, Hans Bethe, and Szilárd. Now they're debating at this point about the H-bomb. On a live radio broadcast, Bethe said he tore out what hair he had left at this point. He said, we're talking about how terrible the H-bomb is and how we have to stop it. And Szilárd says, oh, I can think of something worse than an H-bomb. And he thought up the cobalt bomb, and he said, this would ruin mankind forever. And it caught a lot of attention. Newsweek even had the chemist James Arnold run some calculations and reported that, yes, Szilard's idea of a cobalt bomb might actually be worse than an H-bomb. But Szilárd was just that way. He could not stop thinking things and not stop saying them, and then only later caught up with their implications. Here in the 30s, probably about the time they went to see Einstein and do the letter, somewhere in Manhattan, are Eugene Wigner, his pal from Budapest, and Leo Szilard. And that's it. Thanks so much.
We do have time for
questions
questions and
Oh, I'm
comments.
sorry, yeah. Great.
But I'd like you to speak through the microphone because this is being recorded. So, does anyone have something to add? Yeah, you need to talk in front of it. Anyway, okay. So, all right, we have a user.
Yes, sir. Sorry, I forgot about the question. Love to take questions.
Fascinating history, fascinating period. One of the perennial outliers from the rest of the scientists was Edward Teller.
Right.
I'm curious if you could give us some insight into how he and his own views and his own activities interwove with everything else that his colleagues were doing and urging at the time.
Szilárd and Teller were very fond of one another personally, and they collaborated early on. Teller in 1939 was at George Washington University. I think Gamow was there as well. And Szilárd was in New York with Fermi at Columbia. So when they started hearing news about the possibility of fission, Teller became Szilard's agent, where at George Washington and at the Department of Terrestrial Magnetism of Carnegie, they were actually testing some of these theories. So they were collaborators. When Szilárd drove out to tell Einstein about chain reactions, he never drove a car, so Wigner was his first chauffeur, And then once they decided to send a letter to the president and Szilárd drafted it, the second time he drove out, Teller was his chauffeur. And Teller said, "I only entered the atomic age as Leo Szilард's chauffeur." But of course, he was very active in a lot of important things in science in the late 30s on his own, before he even got involved with weapons. During the war, General Groves would never let Szilárd near Los Alamos, so he never had a chance to interact with Teller. And after the war, Szilárd and Teller divided seriously over whether you could trust the Russians and how you might control a nuclear arms race. They were deep personal friends, and they respected each other. In fact, Teller was in league with Louis Strauss, who in fact set him up as a witness for the Oppenheimer security hearing in '54. And at that time, Szilárd took a plane from New York to Washington to try to reach Teller and tell him not to testify. But he couldn't find him. They had locked him up that night. So he went back and he told his wife, Trudy, "If I can't find Teller, I'm going to have to defend Oppenheimer the rest of my life." And he didn't want Teller to testify. And then Strauss tried to get Teller's mother and sister out of Hungary in the 1950s and had no luck at all, pulling all the big strings he had in Washington. Szilárd, at a pugwash meeting in Vienna, talked to a scientist from Hungary and explained the problem. And he said, "I'll see what I can do." And the next thing you know, the Teller mother and sister were out. Teller appreciated that, but he also did not appreciate that a communist had helped him bring out the family. In 1960 and 61, Szilárd and Teller debated about nuclear arms on television a number of times, and they remained personal friends to the end of Szilárd's life. Yes, ma'am.
Yeah, you touched very lightly on his relationship with the media in a couple cases, but I was just kind of curious, it sounds like he got shut down a lot by, Groves or, stifled or something, and I'm wondering, did he ever do sort of, this is kind of a Snowden, did he ever even contemplate going against these restrictions? And if not, why was that the case?
Well, he was in a curious position. I mean, he thought, mostly correctly, that he saw the realistic situation. But he was a naturalized citizen. He was not a citizen until 1943. And in 1942, when Groves took over the Manhattan Project, he tried to have him incarcerated as an enemy alien. Went as far as the Secretary of War's office to make that request, and Compton and other people talked him out of it. But there was animosity. Szilárd thought that Groves was an idiot, and Groves thought that Szilárd was a Jewish, pushy busybody who was a troublemaker. And so in that way, they were at odds all the time. Szilárd was followed by agents. Is that the time? So he was followed by agents that Groves had put on his tail. And after the war, Szilárd quietly had him fired from the atomic work, freedom to take up biology. And then, actually, he hated Szilárd so much that he went around talking to encyclopedia editors and saying, "Your entry on Szilárd is too big. He's not a famous scientist. He's not worth the record." And then in the middle of the Oppenheimer hearings, 1954, he's sitting there, and Groves goes into a 2 or 3 page soliloquy, if you'll read the transcript, on the troublemaking scientists he had during the war. He had Szilárd in mind, and he said, "If this were Germany, we would have lined him up and shot him." So Groves and Szilárd were like oil and water all the time they were together. Thank you very much.
Thank you. I neglected to mention one of the most relevant facts about Bill Lanouette. He's the author of the only biography of Szilárd, and a marvelous book. It's wonderful reading, so let me give it a plug here, although that's against APS policy. Okay. Our next speaker, Dick Garwin, plays a unique role in the science community. He is an excellent scientist. He was a student of Fermi. He did early work on parity violations. He helped carry out the CERN muon G-2 experiment, which was a classically beautiful experiment in nuclear physics. In fact, he's going to be giving an invited talk tomorrow afternoon on that experiment. In addition to leading a career in science, he's led a career in advising the government, and he is undoubtedly the most respected advisor, who is respected by all branches of the government which turn to the physics community for technical advice or advice on issues in which the sensibility of a scientist is important. I don't want to start going through the details of his career because there wouldn't be any time for his talk and he would probably be embarrassed. But it's always a privilege to meet Dick Garwin, and now it's a privilege to introduce him.
Thank you, Dan. Okay, so you're hearing at this session from three people who knew Leo Szilard. Now, the secret is Bill Lanouette never met him, but he knows him better than anybody else. I'm very grateful for the opportunity to know Leo better as a result of giving this talk. So the Lanouette biography tells it the way it was, incredible though it may seem. And the collected works of Leo Szilard by Bernie Feld and Gertrude Weiss Szilard, editors, give the source material, both published and unpublished. His 1929 paper, little noticed at the time, on the decrease of entropy in a thermodynamic system by the intervention of intelligent beings, looked at Maxwell's demon, which had been looked at quite a lot before, from the 19th century. And it spawned much subsequent research, but not right away. It connected what we now call a bit of information with a quantity k log 2 of entropy, and showed that the process of acquiring, exploiting, and resetting the information in a one-molecule engine must dissipate at least kT log 2 of energy at temperature T. His work on physics and technology demonstrated an astonishing range of interest, foresight, and practical sense. I illustrate this with several of his fundamental contributions to nuclear physics, the neutron chain reaction, and to nuclear reactors, and also to electromagnetic pumping of liquid metals. Now, I met Leo Szilard quite a few times at Chicago. I visited his lab after the war. He didn't work on nuclear physics anymore, or nuclear power, or nuclear weapons. He had actually been denied entrance to or joining the Fermi Institute, and moved to biology. So I visited him and Aaron Novick. They showed me their chemostat, which was a remarkable invention, and they used it. They told me that they had feared that the coaxial cables with polyethylene insulation would be immune to degradation by bacteria, but they had trained bacteria to eat the stuff. Well, actually, they directed the evolution of microbes by manipulating their environment in the chemostat. Edward Teller told me at a dinner party in Chicago of the high regard in which he held Leo Szilard. He said, the way I use Freddie D. Hoffman for calculations at Los Alamos, that's how Leo uses me. Leo Szilard's ingenuity and inventiveness outclassed those of Edward Teller. I learned from Lanouette's book that Leo from the beginning was a would-be social engineer, devising schools, political organizations, even systems of money to avoid or solve society's problems. After the wartime work was largely done at Chicago in 1944, Leo had time to think further about the implication of the nuclear weapon soon to be tested at Alamogordo. That led him to a lifelong career in arms control in which he was uniquely and personally involved. I had moved to New York in December of 1952, and so at the time of the Cuban Missile Crisis 10 years later, Leo called me and asked me to meet him in Manhattan at a small restaurant for dinner. The newspapers were full of the charge that the Soviet Union had installed nuclear-armed rockets in Cuba, and Leo and I politely disagreed on the likelihood. He felt that they would not have done such a thing because they had nothing to gain from it. My position was that they probably had installed such missiles because they had nothing to lose. Of course, we were both wrong. The Soviet Union had installed intermediate-range nuclear missiles, and they did have a lot to lose from it. The crisis was peacefully resolved with the Kennedy administration withdrawing U.S. nuclear missiles from Turkey and Italy as a never-admitted compensation for the removal of Soviet nuclear weapons from Cuba. When I was at CERN for the year, I encountered Leo having an espresso in the cafeteria. We arranged to meet for dinner at the Café de la Gare, maybe it's the Café des Eaux Vives, I forgot, on the left bank. I recall that Leo ate only green beans for that dinner. Our topic of discussion was his suggestion to publish lists of ranking of cities so that if the Soviet Union destroyed a U.S. city during nuclear war, the U.S. would have the right to respond, or at least the expectation of response, by destroying the equivalent Soviet city. I suggested the response should be the destruction of a city half as valuable, which would have comparable deterrent effect, but would, at least if continued indefinitely, result in finite rather than infinite destruction, limited to twice the value of the city first lost. But now for the meat of the discussion. Leo Szilard was an intensely practical person as well as a visionary. Oh, this will be posted tomorrow on my website, so you'll be able to find it. He saw immediate solutions to problems, but confident that the problem could be solved, he looked many steps beyond to the applications. So with Einstein, as you heard, in 1930, he patented an electromagnetic pump with no solid moving parts. It would pump without the wasteful eddies and turbulence characteristic of previous approaches to electromagnetic pumping. This was proposed for use in household refrigerators, but as you heard, was too noisy. How he did this? Well, they had a ferromagnetic core, and the liquid metal was around the core and could have a circulating current driven by a transverse magnetic field, so more or less uniformly. He worked with the General Electric Company of Germany to put this invention into practice, and touted the absence of noise from rotating machinery. But it was not a success. And of course, for household refrigeration, the competition was sealed units with the motor inside and glass or metal feed-throughs, and even those could have been replaced. But they patented an intensely practical absorption refrigerator, and of course, many people worked on that, whether that derives from their patents or not, but it's used widely in the world. Early on, Leo deduced that if he were to achieve his potential, he would have to avoid domestic ties and the drag of possessions, including a home. So he lived in hotel rooms and later in faculty clubs almost his entire life. He would communicate with physicists throughout Europe and Great Britain and would call them by telephone or communicate by mail or telegraph. He learned immediately of Chadwick's discovery of the neutron in 1932, and that year read H.G. Wells' The World Set Free, a novel published in 1914. In 1933, Leo was living in the Imperial Hotel on London's Southampton Row. I've stayed there a number of times myself. Waiting at a traffic signal to cross the road, he was pondering a recent comment by Lord Rutherford, published in the Times of September 12, 1933. We might, in these processes, obtain very much more energy than the protons supplied, but on the average, we could not expect to obtain energy in this way. It was a very poor and inefficient way of producing energy, and anyone who looked for a source of power in the transformation of the atoms was talking moonshine. So Rutherford was correctly referring to what happens with charged particle-induced nuclear interactions in material, cold material. And the energy is predominantly lost by a factor 10 to the fifth or more to electron excitation rather than to nuclear reactions. So Szilard, I missed a sentence here. Szilard thought about this for days, and then waiting for the traffic signal, he had worried this statement not quite to death, but to an advanced state of ill health. He asked himself why there should not be one of the elements which, when exposed to neutrons, would undergo a nuclear reaction that would produce two neutrons. He immediately conceived a search for such end-to-end reactions and decided not to enlist the know-too-much physicists, but to look for a willing chemist to help him. He realized that neutrons don't suffer from the problem that charged particles do. They don't lose any energy at all. And they may lose energy, but they still get absorbed, and they end with a nuclear reaction, every single one of them in matter. He filed a patent application in the UK, requested that it be kept secret, never did obtain the promised £2,000 to explore the periodic table, having mentioned beryllium, uranium, and thorium. I have, but I'll check. General Electric USA told him that his larger issue of power production, the chain reaction, is so far outside the scope of a company's normal activities that unless the proposition takes some much more definite shape, it would be impossible to participate. So this was before the establishment of fission in December of 1938. Leo was not idle, though, and with no background in nuclear physics, immediately began to exploit the neutron. His first paper in the field with Chalmers in 1934 took advantage of the perception that a nucleus that suffers a nuclear reaction would recoil to such an extent that it would break its chemical bond. They worked with ethyl iodide, added a little bit of free iodine, and demonstrated that a large fraction of radioactive material created by exposure to neutrons could be extracted from the ethyl iodide as free iodine. This constituted a new and effective means of isotopic separation and established a convenient and powerful tool for research and production of medical isotopes. Then they used their ethyl iodide preparation as a neutron detector to demonstrate that beryllium produced neutrons under the influence of radium gamma rays. And in December 1934, by the use of bromoform, that is tribromomethane, arranged to be exposed to the radiation from beryllium excited by 1.5 megavolt X-rays in Berlin and flown from Berlin to London. Nothing special about nuclear gamma rays. X-rays from accelerated electrons work just as well. So they separated radiobromine from the stable chemical to show that the neutrons were produced by beryllium by energetic X-rays. In 1935, Szilárd and Chalmers noted that a 4-hour neutron-induced radioactivity in indium was not sensitive to the presence of water, hence not due to slow neutron capture that Fermi had capitalized on in Rome, and discovered the metastable indium-115 336 kilovolt isomeric activity excited by inelastic scattering of fast neutrons. In 1935, he published the only paper in nuclear physics for which he had no collaborator. His point was that neutrons not absorbed by cadmium, so superthermal, generated radioactivity in indium a 54-minute period, and this was induced radioactivity was due to neutrons that are strongly absorbed by indium. This was the first indication of resonance absorption. So they weren't absorbed by cadmium, but they were absorbed strongly by indium in the resonance line. In the pre-fission era, Szilárd had 2 more papers in which he pioneered the use of a neutron howitzer, that is, thermalizing in paraffin with a lead plug that would allow neutrons to come out but would shield the detector from the radiation from the radium source. That elements from atomic weight 35 to 200 give similar numbers of gamma rays when they capture a neutron. And with Goldhaber and Hill, Szilárd pins down the excited metastable state mentioned before, showing that it can be produced from indium-115 by 2.5 MeV neutrons, but not by strong sources of photoneutrons with energy 10 times lower, naturally, because it's 336 kilovolts, which wasn't known at the time. In the post-fission era, his first paper of April 1939 with Walter Zinn, Instantaneous Emission of Fast Neutrons, used a helium-filled ionization chamber to establish that the delay time for the instantaneous emission from uranium was less than about 1 second. Of course, the neutrons are most of the neutrons are produced in the fission process, where the excited nucleus boils off not only the 2 fission fragments, but the neutrons as well. They also established that any delayed neutrons constituted less than about 0.1% of the fast neutrons, with the unstated and wrong assumption that the delayed neutrons have the same energy spectrum as the instantaneous neutrons. Then in February 1940, he had a massive submission to the Physical Review, Divergent Chain Reactions in Systems Composed of Uranium and Carbon. This was after his summer 1939 correspondence by mail with Fermi, who was spending the summer at Ann Arbor learning about cosmic rays. In this long paper, Szilárd identifies the design criteria for a reactor consisting of a large sphere of carbon in which is embedded small spheres of uranium or even uranium oxide. Fermi and Szilárd and lots of other people recognized that a homogeneous mixture of uranium and moderator, natural uranium, could not have a chain reaction because as the neutrons were slowing down to be captured in the 0.7% uranium-235 at thermal energies, they would traverse the resonance region of the uranium-238. And they conceived the idea of separating the uranium and the moderator. Fermi favored sheets of uranium, parallel sheets, but Szilárd established that a three-dimensional separation, a lattice, was better than sheets. The purpose envisaged for the reactor was to produce heat, for instance, to power submarines, but really it was to establish the chain reaction. At that time, the only route to a nuclear explosive was thought to lie in the isotopic separation of U-235. But soon after the February 1940 manuscript, this is a side thought, that's why it's indented, Szilárd received a May 1940 letter from Lewis Turner from Princeton suggesting that U-239 after 2 beta decays forms 94-239, plutonium-239, which is likely as fissile as uranium-235. This was the first inkling of the possibility of plutonium weapons, the utility of a natural uranium reactor in which the loss of neutrons to resonance absorption was not simply an impediment to criticality, but a potential source of useful plutonium, and ultimately, to Szilárd's fertile mind, to the possibility of a uranium-plutonium breeding cycle that could convert most of fertile natural uranium to useful heat. So he figures in this 1940 submission, which he also asked be kept secret and not published, the critical radius of the reactor is sensitive to thermal neutron absorption cross-section of graphite and its density. So for reasonable assumptions, about 100 tons of graphite and 30 tons of uranium. In the Szilárd papers, there is a speech of 1946 where he says at Chicago, "I felt that even if a chain reaction could be maintained in a uranium-water mixture, we would have to deal with the very disagreeable chemical processes in such a system if we attempted to use it for the liberation of atomic energy on a large scale. The radiations emitted from uranium would decompose water into hydrogen and oxygen, and this explosive gas mixture would have to be removed." But really, both heavy water and light water reactors work all over the world, some of them with catalytic recombiners, some without. Once the uranium-carbon reactor approach was accepted, Szilárd in large part left the details to others. He was not much of an experimenter, but he was superb as an idea man. He was not only instigator, but chief troubleshooter for the project at Columbia and Chicago. So he invented the fast neutron breeder reactor, in which he found an application for electromagnetic pumping of molten metal coolant. He was willing to talk to anyone to learn of problems. Now, the problems were at Chicago to realize the reactor method of producing plutonium. And then after Los Alamos was established in spring of 1943, to send the materials from the still-to-be-built reactor in Hanford to Los Alamos. So he has a 3-page document, important from the point of view of building reactors and nuclear explosive both. People made uranium powder by calcium hydride reduction process, but once they had the powder, it was impossible to fuse into a solid because of thin oxide layers on the surface. This was early 1940s, remember. Furthermore, some batches were pyrophoric and others were not. Upon making inquiries, Szilárd learned that it's customary to protect tungsten powder from surface oxidation by coating it with a thin layer of paraffin. So he worked with Alexander, who had prepared the uranium powder. They coated it with paraffin, then they drove off the paraffin and compressed the material, achieved by heating a fused uranium ingot with density exceeding 18 grams per cc. He published a memorandum evaluating bismuth, helium, hydrogen, and air coolants for a reactor. He envisioned a power plant producing 300 megawatts thermal. Looking still further ahead, in July 1942, remember the reactor had not been demonstrated until December 2nd, 1942, returned to his work to scope the question of electromagnetic pumping for a bismuth-cooled production reactor. And then about a week before the successful operation of the Fermi pile, he estimated that such a unit would produce about a kilogram per day of plutonium-239. So I'd like to talk about fast neutron breeders, but I don't have time. And now about his famous 1929 paper, which aroused much later such a storm and was so productive in understanding information and entropy. Well, first, Szilárd sketched in his 1929 paper the Maxwell demon. And then he decided that it was easier to analyze a couple of other cases. So first, a single molecule engine sitting in a cylinder in which was divided in two by a frictionless and weight-balanced piston. The experimenter notes on which side of the piston the molecule finds itself and moves the piston slowly away. So the gas expands and does work on the piston. You remove the piston, or you tilt it or valve it, and you reinsert it again to divide the cylinder in two, determine which half the molecule resides, move the piston away. You can have a piston that goes only one way, if you like, and you just have it operate only half the time when the molecule is below it and the piston goes up. For those discomfited by a gas consisting of a single molecule, Szilárd considered a totally different approach in which a finite cylinder contained a mixture of two gases and two semi-permeable pistons, or movable membranes, as well as two opaque pistons. Now you can have macroscopic pressures, and this works just as well because you're not identifying individual molecules and telling them what to do. But the trick is that the molecules can, without any energy expenditure, be told to change their state so that they are now permeable or impermeable to the piston. As noted by Lanouette in his presentation, such an approach is now used for practical purposes of cooling and compressing groups of atoms and molecules, and you convert from one to another by adiabatic rapid passage of near-resonant laser beams, and so you change the spin orientation, and so the semi-permeable membranes are magnetic walls or laser walls. Either one, they work equally well. Now, Szilárd and his peers, referring probably to Szilárd's dropping in on him at Columbia University around 1935, Robbie is quoted, "Szilárd kept telling me which experiments I should conduct. Finally, I said, Leo, if you really think this is so important, do it yourself." Of course, he never did. In the construction of the exponential piles in Pupin Hall at Columbia, all pitched in to pile the graphite blocks except Szilárd, who hired a Husky undergraduate to do the work for him. Ever the first to lead his team by actually doing things himself, Fermi was disconcerted by this initiative. He knew there was something wrong with it. Eventually, George Pegram, dean at Columbia, saw the merit of Szilárd's approach and pressed the Columbia football team into service. Nina Byers recalls that Szilárd and Fermi were not on speaking terms when she was a graduate student at Chicago, 1950 to 1956. And in fact, she was invited by Szilárd to report on the substance of lectures Fermi was giving on isotopic spin and pion physics. In her interesting and accessible memoir, Byers quotes Szilárd, "Fermi is a scientist pure and simple. This position is unassailable because it is all of one piece. I doubt he understood that some people live in two worlds, like I do. A world, and science is part of this one, in which we have to predict what's going to happen, and another world in which you try to forget these predictions in order to be able to fight for what we would want to happen. Finally, Ted Puck, a biologist in those days in Colorado, in Szilard's days as a biologist, explained in a December 1955 letter why Puck would not offer him a position in his lab. You have to understand that Szilárd never really had a job, and he didn't want money, he just wanted enough to live on. But he would try to put together visiting fellowships and whatever, but the sticking point was that he was always asked not so much what he would do, which you're asked these days, but how much time he would spend at each institution, and he refused to say. So he had always was living quite marginally off other people, getting enough money one way or another. In December '55, Puck admitted that no permanent post would be offered in Denver. With the greatest possible reluctance, I've come to the conclusion it's not possible for me personally to work with you scientifically, he wrote Szilárd. Your mind is so much more powerful than mine that I find it impossible when I am with you to resist the tremendous polarizing force of your ideas and outlook. Puck feared his own flow of ideas would slow up and productivity suffer if we were to become continuously associated, working in the same place and the same general kind of field. Puck said, there's no living scientist whose intellect I respect more, but your tremendous intellectual force is a strain on a limited person like myself. Szilárd recognized early that he had far too many ideas to work them all out himself. His batting average was high, but even superior mortals such as Fermi and Rabi found their approach to science threatened by Szilard's insightful suggestions. They valued thoroughness and completion of what they started. On the other hand, we have Robert Browning's view, but a man's reach should exceed his grasp, or what's a heaven for? Szilárd strived to help mankind in general, and he also cared deeply for individuals. Though dismayed with Edward Teller's 1954 testimony in the Oppenheimer affair, and letting Teller know it, he still intervened to obtain the release of Teller's mother and sister from Hungary. I think that Leo Szilárd was happy and cheerful despite his self-assigned mission to reform the world. I close with his comment, characteristic of his views. With this remark of Turner on plutonium, May 1940, a whole landscape of the future of atomic energy arose before our eyes. And from then on, the struggle with ideas ceased, and the struggle with the inertia of man began. Thank you. This is my website, fas.org/RLG/. You can find all kinds of interesting things there. Microphone.
At the big Centennial Conference at Atlanta, where you helped Hans Bethe up the steps, I recall he made one statement, it was a short statement, but it was that before coming to America and getting Einstein to write the letter, he had tried to have a meeting with Churchill, and Churchill dismissed him very impolitely. And I asked several historians, I'm not one, had they ever heard of anything about that?
Oh yeah, Bill Lanouette has that. Bill, would you like to comment? Because I can't do it right. Come over here. Oh yeah, go to that microphone. Good.
Before Szilárd moved to America in '38, I found no record of him approaching any politicians. He did approach the Army, and they dismissed him. They thought that this idea of chain reactions had no practical purpose. Almost as a courtesy, F.A. Lindemann, who was a science advisor, asked the Admiralty to make it a secret. I found no interactions with Churchill by Szilárd although he did try to influence a few members of parliament here and there.
In fact, Churchill also had read the Wells book. Get up and cue up to the microphone. And by 1931, before the neutron was discovered, Churchill was looking for atomic bombs of one kind or another. Please go to the microphone.
I wonder if the remark about Churchill, excuse me, is confusing with Bohr's meeting with Churchill in the spring of 1944, which was very ill-fated business.
I think Beta said that it was before he came to America.
No.
Beta really
Other questions? Yeah, go ahead.
I would be fascinated. It may, in fact, happen, and there's just no record of it. Szilárd and Beta knew one another in 33 and 34 in London, and at that time, Beta was just amazed by Szilard's activities and by his ingenuity. There's no written record of any comment or any contact between Churchill, but who knows? Szilárd tried all sorts of things.
So, Szilárd was a chemical engineer by training, and so he realized in the question of graphite as moderator that there might be an impurity. There might or might not. Maybe carbon did have an appetite for neutrons. So he talked to the people who were making graphite in the United States, and he said, is there any way that some impurity, maybe boron, would get in? And they said, funny you should ask. We use boron carbide electrodes. And so could you make it without? And he said, yes. And that's how the United States had a graphite moderated plutonium production pile and the Fermi pile demonstrating, whereas Heisenberg's crowd in Germany rejected graphite and had to use heavy water as a result with natural uranium. And lots of difficulties getting the heavy water, some of them imposed by the Norwegians, some of them by the Allies. Yes?
Your last remark leads to an interesting question. One thinks of him, especially here, as a physicist, but you've drawn a light to his activity as an engineer. Would you like to comment upon this interesting and strange intersection between his practical knowledge and his engineering skill, and then his insight into fundamental principles? It seems very extraordinary that one person had two such very diverse abilities.
It is quite unusual, and so he was, highly theoretical, as you could see in his work on the Maxwell demon. But even there, he had practical insights as to pistons and gases and semi-permeable membranes. So Fermi was both an excellent experimenter and a theorist, but he did not have the range of ingenuity and passion for applications that Szilárd did. Fermi, when Fermi got a Nobel Prize in December 1938 for the efficacy of slow neutrons in causing transmutations and for transuranic elements. Well, he had made transuranic elements, but that wasn't what he was seeing in his experiments in Rome. He was seeing fission products. And so it took the Christmas insight into fission as the source. And Szilárd, when Fermi got off the boat, met him, and also, I guess, Fermi met Bohr in January 1939, and the idea of fission spread in a couple of days. But Szilárd immediately pushed Fermi to chain reaction to nuclear weapons, and Fermi really just wanted to study fission as a physical phenomenon. So Szilárd wasn't distracted by that. He had invented nuclear weapons and nuclear power in 1934, and he was going to pursue it. He pushed Fermi to do that. So, thank you.
Thank you. Our final speaker, Matthew Meselson, is a distinguished biologist who is professor of biology at Harvard University. He has received many awards for his research in biology, including the Lasker Award and the National Medal of Science. He has also devoted his career to the problems of controlling chemical weapons and biological weapons. We're very pleased that he is here today to talk about Szilard's role in dealing with these problems.
Thank you, Dan. And the Leo Szilard Award, as a matter of fact, from this society. So I met Leo first as an undergraduate student at the University of Chicago. And at that time, the way in which I knew Leo was that he was advising young physicists as to whether they should go into biology or not. It was a time when many more students were accepted into the PhD program in physics than were allowed to be graduated. And so there was a lot of interest on the part of young physics graduate students as to whether they should in fact become biologists. And Leo was available and talked to quite a few my friends who, some did become biologists, some didn't. Some stayed in physics. One of those was Nina Byers, who Dick mentioned. She stayed in physics. Leo got busy in biology in 1947, really. He took the summer phage course at Cold Spring Harbor that was taught by Max Delbruck and Salvador Luria. Small, hands-on course, how to work with bacteriophages. Together with his much younger associate, Aaron Novick, who had been in the Manhattan Project, Leo established a lab at the University of Chicago, or I should really say in an abandoned synagogue, where they established a lab, while Leo had an appointment at the university as a half-time professor in the Institute of Radiology and Biophysics there. And one of the first things they did was to think about how could we isolate a lot of mutants in bacteria that might be interesting to study if these are mutants which keep the bacteria from growing very well. Sounds paradoxical. And this led to the idea of the chemostat, in which bacterial growth duplication rate is strongly limited by the availability of an essential nutrient, a carbon source. So that a mutation, unless it affects the uptake of that essential nutrient, won't affect the doubling time of the bacteria, but it might be a mutation which in free growth would be detrimental. So in this way, they were able to get around the selection against a deleterious mutation and get a lot of interesting mutations to study, and also to measure the temperature coefficient of the mutation process, and also whether it depended on time or on the number of duplications, and they produced a lot of interesting data. This is a subject that is still somewhat not understood, but this was the beginning of a long series of experiments done by Leo and Aaron with the chemostat, which, as Dick said, was an impressive experiment, bubbled in tubes and very pretty. When he was at Chicago very early in 1948, he was a leading person to organize what was called the Midwest Molecular Biology, no, I guess it was called the Midwest Phage Group. And Salvador Luria used to come down, Josh Lederberg was a member, Al Hershey, Jim Watson. They met monthly and talked about problems in molecular biology. With Aaron Novick, Leo did a remarkable series of experiments, including the chemostat experiments, but some others as well. They discovered that visible light would reverse the effect of ultraviolet light in causing mutations in bacteriophages. The mechanism that they proposed for this was wrong, but the discovery was right, and it took another 20 some odd years before it was figured out just why visible light can reverse the mutational effects of ultraviolet light. By the way, one of their papers using the chemostat to study spontaneous mutation, if you look in the electronic indexes of publications, you can see how many times it was cited in another publication, and by now that's reached a number over 500 citations of that major paper using the chemostat to study mutations. They also discovered that if you infect bacteria with two kinds of viruses, some viruses come out with a protein coat of one and the DNA of the other. The DNA, that is the inheritance. And that showed, was one way of showing that it's the nucleus. Sounds silly to say now, but in those days we weren't sure, that the DNA is what determines the structure of the protein. They closed the lab in 1953, and Leo said that he was going to become a roving theoretical biologist, which is what he became. And much more than that, of course, as Bill has told you about. But he kept on publishing papers in biology. In 1958, he published in the PNAS the first mathematical theory on the nature of the aging process based on reasonable molecular assumptions. It was wrong. It was based on the idea that it's damages to chromosomes that cause aging. Now, it's almost certainly not the case, but it was the first paper which took a serious approach and has been reviewed a number of times, even recently, because it did start. Leslie Orgel then wrote the next paper on this subject. The serious molecular biological study of the aging process. We still don't know what drives the aging process. Probably not telomeres. So, and then they discovered that, you know, in biochemistry you often have a series of enzymes which, down a chain, take a precursor and convert it to one compound, then another enzyme converts that to something else, another enzyme converts that to finally you get a usable end product like an amino acid, like tryptophan. There is such a chain, a reaction chain that produces the amino acid tryptophan. And Leo and Aaron discovered that if you add tryptophan to such a reaction system, it inhibits the first enzyme in the chain, which is intelligent because if you've got enough tryptophan, you should tell the whole chain, not just one enzyme, but the whole chain to stop working. And that is achieved by having the first enzyme in the chain stop working until there's no more tryptophan, and then it is no longer inhibited. But this idea of negative control must have been in Leo's mind in an important lecture he gave in Paris. Now, here I need to digress a little bit. Jacob and Monod and Pardee had discovered, I won't describe the experiment, but that there's a certain gene which, if you knock it out, causes the intense production of a group of enzymes. So here you destroy a gene, and a whole bunch of enzymes get produced at high rates. And Jacques Monod's view was at that time that the control of enzyme production, the control of turning genes on and off, was a positive kind of control. In other words, that you had to put some kind of control protein onto the DNA to turn the gene on. Leo had the opposite view. He had the view that if you knock out a gene, it sounds like you're knocking out something that's preventing the production, because when you knock out this gene called the I gene, production goes way up, and so if you knock out something, it must have been holding the production down. It's a repression, it's a negative control. And this was proposed in this lecture, and there's no, so far as I know, there's no record of the details of that lecture. I'm really only imagining, but I think it has to be right, what Leo would have said, thinking about negative control. So this was cited in both the paper, the very famous so-called pajama paper, named after the first initials of Pardee, Jacob, and Monod. Actually, aficionados call it pajamo, but some people like it called pajama. Anyway, this very famous paper, which is the first paper to show how genes are controlled. They're controlled by something which lands in a group of genes and prevents their expression, a repressor. So at the end of that famous paper, the pajama paper, it says, quote, "We are much indebted to Professor Leo Szilard for illuminating discussions during this work." That's quite unusual. Most people in my field aren't that generous anymore. We used to be. And then when Monod got his Nobel Prize in 1960, that long ago? Yeah, 1965. Yeah. Anyway, in the text of his Nobel address, we find these words. This is precisely the thesis, namely negative control, that Leo Szilard, while passing through Paris, happened to propose to us during a seminar. We had only recently obtained the first results of the injection experiment, that is the result of knocking out a gene and the enzymes turn on, and we were still not sure about the interpretation of this experiment. I saw that our preliminary observations confirmed Szilard's penetrating intuition, and when he had finished his presentation, my doubts about negative gene control, Jacques always at the beginning didn't like negative controls, my doubts about negative gene control had been removed. So Leo had a big impact on that work. In another way, not experiments, but stuck together. Leo kept on writing papers, theoretical papers, a paper on the nature of memory and aging based on ideas about how neurons are interconnected. Some papers he didn't actually publish. One of them, which I like a lot, is he thought it's important for parents to recognize their children, and maybe for children to recognize their parents, because we pass our genes on, we'd like them to do well, and the genes would like to do well anyway. And so maybe the genes that determine what your face looks like are all linked together on the same chromosome. And today it's still, so far as I know, not known whether the genes that determine how you look happen to be linked close together on the same chromosome, so they won't be separated in future generations by genetic recombination, but it keeps them together. So that's an interesting question, and we can begin to answer it now. I don't know if anybody is trying. I talked to a fellow in New York who's building a huge new sequencing effort in New York City, and suggested to him that this is one thing they could do that would at least get them in the newspapers, which they won't have any trouble doing anyway. So, and he wrote a number of other papers which he circulated, always published in good journals, PNAS, Science, Nature. Leo was an organizer of biological research entities. The first was the European Molecular Biological Organization, which is now a huge organization. While at CERN, he proposed this idea to some of his friends there, I think Vicky Weisskopf and a few others, who then approached some biologists, Kendrew and Crick in England, and Sidney Brenner and Jim Watson, and they had a meeting in Ravello in Italy, and they decided to try to create such an organization that would be European and not international, that it would have also a teaching role, not for undergraduates, but for graduate students, advanced courses, fellowships, etc., and they called it the European Molecular Biology Organization, or EMBO. Today, there are 20 states, European states, who are members of EMBO, contribute money, they receive benefits. The main lab is in Heidelberg, and there are 100 different principal investigators there. It's a big place. There's another lab in Germany as well, and a lab in France, and a lab in Italy, all part of EMBO. And the library at the main site in Heidelberg is called the Szilárd Library, named after Leo. The Salk Institute at La Jolla came about, I would say without Leo, it would have been very different if it had come about at all. He had an earlier plan with his friend William During. They were both interested in limiting birth rates and population bomb and all that, which was a problem then. Maybe it's not going to be a problem. We read now that maybe reproduction rates in most countries are really dropping down to low levels. But anyway, they were interested in creating two institutes, and they drew up a detailed plan. Leo's plans were always detailed, for a public health research institute, and then another institute which Leo called the Institute for Problem Studies. So you can do whatever you want. That's what Leo would like to do. And they asked Jonas Salk to be, various people to be members, and they went to Jonas and said, we'd like you to be a member. Nothing came of this, but it did establish a connection with Salk. And at the same time, Salk was trying to get the University of Pittsburgh to set up a new institute for him. And Leo told him, look, good scientists, the best scientists, could be more easily attracted to Southern California instead of Pittsburgh, and you ought to do it there. And so this began a whole series of meetings at the Hotel Carlyle in New York with great piles of lox and bagels and coffee and so on. I used to go to those meetings. I didn't go to Salk. I was part of that group, but I decided to move from Caltech to Harvard before Salk could be ready. But there, Melvin Cohn and Seymour Benzer and Ed Lennox, Ted Puck, Leo, developed over the time Leo's idea for how it should be run. And his idea was there should be no board of trustees, be run completely by the scientists. Later that got changed. I guess scientists aren't that good at raising money. Boards of trustees are for that purpose. But Leo thought that it would be wiser if the scientists at least ran the science. Leo moved as a full-time member of the Institute to La Jolla, and he and Trudy Szilárd lived in a nice little sort of cottage behind the Del Charro Motel there in La Jolla near the Institute. And on May the 29th, I was having dinner with Leo and Trudy, the three of us, and there was a table in front of us and all kinds of things. And Leo had a very chaotic way of mixing things. When he ate, he'd put mustard and stuff and salt and vinegar, put them in spoons and eat them. He was very unconventional in his eating habits. We were watching TV. It might have been something like Bob Hope. It was a very unintellectual evening. And then at the end of the evening, I drove back up to where I was staying in Los Angeles, and that morning I learned that Leo had died in his sleep that same night of a heart attack. He was 66. So now Leo is a peacemaker. I've been assigned to talk about both subjects. So you know that right after the nuclear weapon, Congress had to decide what sort of organization to create to develop atomic energy, and one proposal was from Senators Nunn and May. I wonder if that was an ancestor of Sam Nunn? No, Nunn Johnson. Yes, that's right. Why was it called the Nunn-May building? Bill? No. I guess must have mixed them in my head when I typed it, yes. And then there was and in that bill there were the permanent directors, and they could be, they didn't have to be, but they could be both military people. And there were other provisions in it. And Leo and Harold Urey led a campaign of many scientists to oppose that, and instead to try to get the Congress to pass a bill which originally was very much oriented towards open information and scientific administration, called the McMahon Bill. It was modified finally in order to get the Senate voted for it without a dissenting vote, but the House had some opposition. It got diluted a bit, but that's the bill which created the Atomic Energy Commission. As Bill said, Leo liked to go to pugwash meetings. Now there's one pugwash meeting I didn't attend, and so what I'm going to say may be wrong, but I've heard it from several people who were there, that there was a point when the American delegate in Stowe, Vermont, when the American delegation, led by Harrison Brown, a geologist at Caltech, and the Soviet delegation, led by a physicist named Top Chief, so he was the top chief, came to complete deadlock. And Brown said that Americans were going to walk out if there was no more motion. And then in the room was heard, "Da!" And everybody's sense of relief, at least on the western side. They look around, it was Leo, who had been sitting in the middle between the two groups in the story I've been told. If it's not true, it could be true. So it doesn't matter, because it's a good, it is true, so it is circulated widely. So then Leo was diagnosed with bladder cancer, as you've heard, and I think that special therapy was to insert seeds of radioactive isotope, but whatever it was, he spent a long time in the hospital, but he got cured. But during that time, he called Dobrinin, who was the permanent rep of the Soviet Union at the United Nations, and at least this is what I've heard from Leo. Then there's a long memo about it too, but I used to visit him down there. I was at Harvard by then, and I spent a lot of time down there at the hospital with Leo. And I think, well, the story I remember is that Leo said he wanted to see Khrushchev, who was coming to the United States to talk to the United Nations, for 2 hours, and Dobrinin said, "Oh, can't do that. How about a few minutes?" And Szilárd said, "Forget it." And then when Khrushchev arrived, Dobrinin called Szilárd and said, "General Secretary will see you." No discussion about how long. Leo went and got a little gift to give to the General Secretary. And the best part of the story, and Leo has written a long memo about it, but I'm going to tell it to you as I imagine it happened with not the careful prose that Leo wrote. So at some point in the discussion at which Leo had suggested a hotline, didn't come into existence until everybody got scared to death by the Cuban Missile Crisis, '63. But anyway, here's Leo, and I imagine he's there. They're both, little fire plugs of men. And he pulls out this box and he says, "Mr. General Secretary, I have a gift for you. It's a special kind of razor. I use it every morning myself to shave, but it requires special razors. And here in this box, I have a 6-month supply of the special razors. And I promise every 6 months to send you a new supply of the special razors on one condition." "What is that?" Khrushchev might have asked. And Szilárd says, "No nuclear war." At which point, in my imagination, I think it must have happened, one fire plug, Khrushchev, puts his arms around the other fire plug guy and says, "Don't worry, Szilárd, when nuclear war starts, I stop shaving." And so will everyone else. But imagine, Leo, if this isn't exactly what happened, it could have happened, because that's exactly, and part of Dan's idea of this little seminar is to convey the nature, the personality of Leo, and that story does. Let's see, what else? Well, then, after the Cuban Missile Crisis, which scared everybody to death, no, it was before the Cuban Missile Crisis. He wrote a speech called "Are We on the Road to War?" And he went to various college campuses, started at Harvard and went out to California, and gave this lecture, "Are we on the road to war?" And he asked for people to respond to him, and he got quite a few responses, and created then what he called the Council for Abolishing War, which got its name changed pretty quickly to the Council for a Livable World, which the initial idea of which was it would combine two things. The sweet voice of reason, he called it, which was scientists going to the Senate and providing a good lunch to those senators who would listen to the sweet voice of reason about arms control matters, and also would, however, gather from its supporters checks, money, and would collect a pile of such checks, and then allow the director or members of this, or supporters of the Council for a Livable World, to enter a senator's office with what was then considered a significant amount of money. Of course, nowadays, you have to have a lot of money. But the directors and board members, initially Leo and his friend Bill During, who's an organic chemist, and Bernie Feld was a director, George Kistiakowsky, who had been President Eisenhower's science advisor, Dudley Hirschbach, Nobel Prize-winning chemist. I guess you guys keep track of some chemists. Hans Bethe, Ed Purcell, Herb York, now still living. Roy Glauber is one of the directors, and it goes on. And as Bill said, there's a vast archive of Leo's documents, letters, articles, photographs at the University of California in San Diego, and the intention is to, and it's online already, there's some things online, the intention is to put the whole thing online. What about Leo? So if you've heard, he was brilliant, original. I would add he was lovable. What are you going to say? He was. He loved ideas, and he didn't seem to have any interest in taking credit for anything he did. He was a bumblebee who would fly around to different labs and very quickly understand what was going on and fascinate everyone with his ideas, some of which were important in what people then subsequently did. He cared about the future of humanity. He was a wonderful guy. I don't think anyone like him. Thank you. I'd be glad to try to answer questions.
Do we have any?
Don't get me wrong here, but as someone who's raised children in the recent times, I know that if I had a kid that exhibited some of the characteristics of Leo Szilárd, they would be labeled as ADD or bipolar or something of that nature. And I'm just kind of wondering, what do you think would happen? Would it be possible for someone like Leo Szilárd to exist today in today's environment? Could they grow up relatively unmedicated and do the same thing? And I guess also, did anyone ever go beyond saying he was eccentric to anything more of that nature?
You better do that.
Yes, would you?
I think science was very different at the time Szilárd was born and grew up. It was very much more elitist. The fact that he was educated at home until high school, the fact that you could walk in on someone like Max Planck and take a course from him is something that has changed fundamentally with the information explosion and with the public education on such a grand scale in so many countries. I think Szilárd, in a sense, slipped through the cracks. He had a good family background. He went to the right place for an education. And I think he succeeded not only by his wits, but by the way he played the system at the time. I don't recall any people being concerned about his mental health. They thought he was awfully rude frequently. He was self-absorbed frequently. He made jokes nobody understood, and he was a bit of a misfit in that way. But I think psychologically he was just someone so taken with ideas that the rest of the world was on another plane. He was chasing his ideas for his whole life. He would never settle down. He would never take a lectureship position. He didn't have assistants. He didn't get into the organization, but he managed somehow to live outside it and to bounce around and to be at the right place at the right time. Somebody doing that today, I don't know how they would. Would they create a television station of science and declare their views? They certainly wouldn't work up through a PhD program. The system has just changed fundamentally, and at that time, somebody as quirky as Szilárd played it just right.
Well, if we assume that it would have to be a physicist, we could get an upper bound. To take the total number of physicists and make that the denominator, and that's the upper bound. But if there's a genetic component, someday we'll be able to make Leo Szilárds.
I guess this is a question for all three speakers. We've heard briefly about the relationship between Leslie Groves and Szilárd. What kind of a relationship did Oppenheimer have with Szilárd?
I think it was a distant and kind of an uncomfortable relationship. They never crossed paths in California, where Oppenheimer began his his scientific career. Groves would not let him go to Los Alamos, but there was one time in May of 1945 when Szilárd went to the White House and was sent to see Jimmy Burns and learned about this interim committee and learned that in 3 days the interim committee would be meeting in Washington, D.C. So Szilárd went back to Washington, actually went to General Groves' office, and because he knew he could find Oppenheimer there. And he sat down, and by his own account in volume 2 of the MIT papers, he sat down and he argued with Oppenheimer before Oppenheimer was going into the interim committee meeting. And he said that you can't use this weapon, it has no military value, and to which Oppenheimer and Szilárd was arguing for international control and everything else. Oppenheimer said, well, the bomb is shit, meaning it had no military value. But he was still willing to go ahead and use it. And they confronted one another very dramatically. Oppenheimer suppressed Szilárd's petition, and until about a month after Hiroshima in September, when Oppenheimer started to have a change of heart, Oppenheimer was all for the bomb and Szilárd was all against it. The crack he made about having to defend Oppenheimer was more a matter, I think, of personality disagreement. He supported Oppenheimer's opposition to the H-bomb. and such, but there was a prickly relationship, and the two of them, I think, aside from a few exchanges, never really got together.
Yes, would you come?
This is just a comment to perhaps to get a reaction from three Szilárd experts. Of course, there is another Hungarian in a different field, not a physicist, who led life just like this, and that's Paul Erdős, the mathematician, who traveled with a suitcase and would show up and say, if your brain is empty, I'm moving in. And he published hundreds of papers with unexpected collaborators. Now, of course, he was a Hungarian. Now, this says something about the genetics, but you don't have to be a physicist. I wonder if anyone's thought about a parallel biography of these two interesting characters.
Well, it's tremendously hard to write even one autobiography and two together. But yes, but Erdős was a mathematician, and Szilárd was a scientist, but his main intent was social good. He wanted to change the world for the better. And so the parallels part there. And Szilárd had 2 suitcases. He said he kept them packed, and he did this. He said, you don't have to be a lot smarter than the other guy, you just have to be a day earlier.
Okay. Well, so I think this is a good time to wind down. Let's thank Matt Meselson and our other speakers.